We are now starting the public defense in Doctorate of Engineering, Civil Engineering, entitled Model-Based Real-Time Monitoring of Large-Scale Urban Traffic Networks for Decision-Making, presented by the student, Cristian Roviro Portilla Caicedo.
Thank you, Professor. So, hello, everyone. Welcome to the presentation of my thesis entitled Model-Based Real-Time Monitoring of Large-Scale Urban Traffic Networks for Decision-Making. My advisor is Professor Jairo Espinosa, and my co-advisor is Professor Ivan Sarmiento. First of all, I would like to say thanks to the juries, Professor Bardechuter, Professor Satish Kusuri, and Professor Carlos Gonzalez for the time spent in this review process. Okay, let me start talking about the traffic congestion. That is one of the biggest problems that have to solve the modern cities. Some consequences about the traffic congestions are the travel delays, the increment in the accident rate, the noise, the greenhouse effect, and at the end, the negative impact on the quality of the life of the citizens. The most evident cause of the traffic congestion is the situation when the supply is less than the demand. In other words, when the flow of vehicles exceeds the road's capacities. The accidents could be also a cause because of the behavior of drivers and pedestrians and the bad road conditions. For example, in this picture, I present a bad condition of the traffic in the city of Medellin. That was because that day was raining a lot. So another cause is the excessive use of private vehicles that can be explained for the low quality of the public transportation, for example. And at the end, the poor network management that can be an indirect cause of the traffic congestion. So talking about the urban traffic management, I decided to present you this quote of William Thompson Kelvin that said, "What is not defined cannot be measured, what is not measured cannot be improved, and what is not improved is always degraded." I decided to highlight the word measured because the measurements in this case that are the data are so important in the decision-making process. So the problem statement was split in two different problems only for this presentation, but the idea is to split in the problem one, that is when there is a lack of urban traffic sensors, and the problem two, when there are urban traffic data, but that data is coming from different data sources. I'm going to tackle this problem here, that is problem one, when there is a lack of sensors. And the obvious or more evident option is to include or to install sensors networks and communication networks in order to develop a monitoring and management urban traffic system. However, this solution has a high cost of implementation and maintenance. As an alternative, I decided to present Flexi, that is a flow estimation based on collaborative information. This collaborative information is based on waze. Waze is a mobile application that is used by the drivers to navigate around the cities. One way to present the data for waze is for the cities with aggregated information that is called Waze for Cities. In this case, Waze shared the data in order to the cities improve the conditions of the jam conditions. So in this case, it's really important to take into consideration that this is a private company that don't provide information, this kind of information that is a real-time information for anyone. It's also for the government. So with this information, we can transform the waze data that are the speeds and the delays into a more usable information like flows of vehicles and length of the queues. For the problem two, I decided to present here that example is only for the city of Medellin, where there are a lot of sensors that are in the city. For example, cameras, Bluetooth, speed detectors. This kind of data is usually heterogeneous data that, for example, contain main speeds, main delays, flows, and OB information. These data also have different sample times, different reliability, and for example, in some areas could you find redundant information, but in another ones, there is a lack of data. My contribution to the problem 2 is here that was to propose a methodology for the integration of available urban traffic data sources. So there are so many previous works about the monitoring systems, but I come here 3 of that systems that is Stratos was created by Siemens, Einsum Live that is one for Einsum, and counting and traffic monitoring that is offered by Hypo. That these all of these softwares are coming from private companies and provide services for the cities, but you have to pay for them, and you have to take more ads or more upgrades to implement, for example, collaborative information that is not included in these systems. But the important thing here is that the data must be fused for the implement monitoring system. There are a lot of works related with the function implementation. The objective of these works is, for example, the OD matrix estimations, the estimations of the speeds, the densities, the incident detections, and the travel times. The methodologies here are, for example, optimization, Kalman filter, that is a way of optimization also. And that kind of methods allows to estimate some variables combining different kind of data sources like accounts, loops, Bluetooths, GPS, videos, and others. So I want to show you the original objectives of my PhD thesis. The general objective is to propose a methodology to estimate urban traffic network states in real time for decision-making system, taking into account limited information and using data fusion techniques. The specific objectives are to establish relationships among data from online, offline, and collaborative information, to develop a methodology based on data function in order to integrate data for multiple sources within a mathematical model for decision-making, to validate the proposed methodology by means of representative case study, including real data, and finally, to analyze the impact of the proposed methodology in large-scale scenarios by means of simulation using the Sumo simulator. Here I include the both problems that previously I present. So the idea is to develop these problems in this presentation. So the urban traffic monitoring system include both problems, problem 1 and problem 2. Check here that there are several data sources, for example, collaborative information that is coming from waze. That waze is also online, but I decide to split and separate this collaborative information because this information has a particular configuration. That the online information is coming from, for example, induction loops, VDS that are video detection system is with video analytic process, and offline information such as OB matrix and stories. The collaborative information is processed by using Flexi, that is my model, that is an urban traffic model. And another kind of data is processed through data processes like cleaning or resample, or for example, in the case of OB matrix, require the assignment of the OB matrix to the network to find the flows. And in this part is the integration of the data for the data collaborative online and offline data through data function techniques. And the result, the main result of this system is the balance flow, that is one variable that is more reliable than the other ones. So the outline of this presentation is as follows. First, I'm going to present Flexi, that is flow estimation based on collaborative information. This part of the problem 1. After that, the integration of available data sources, that is part of problem 2, and something about the working of large-scale scenarios, then the conclusions, and finally, the research outputs. Let me start with the first part, that is Flexi. But here I would like to present what kind of data provide waze, that is a waze description, that is, this is a JSON format, and present a really interesting information that is presented for one event. One event is this hit that contains, for example, the length of the event, the location between through geopoints that are printed here in this example. and the speed given in kilometers per hour and the delay given in seconds. Note that the delay is only possible to calculate after that one vehicle crossed completely that event. This event could be moved around the corridor, so it's so important to take in consideration this situation. So note here that the Waze doesn't provide information about the flows or the number of vehicles. It's only this information is an aggregate information, so it's necessary to, for example, if you want to estimate the information in only one link, I means that the connection between two intersections and a street, you need to make some intervention in this data to find this objective. Another thing of Waze is Waze only provide information under young congestions. So when the event here disappeared, the model assumed that the congestion disappeared as well. So this is a simple example of the Waze events here. I present the length, the speed, and the delay. Note that the delay, I told in the moment that I started working with this kind of data, that was an estimation making by Waze. So I decided to explore some alternatives to discover what is that relation. And in the first equation, I present one relation that was coming from the fundamental theory and principles. And I include this parameter that is the free flow speed, that is a parameter that could be estimated from that data using last square method. This is the parameter found. The accuracy is so well, and check it that the model that is presented in equation 1 fit so well the speed given by Waze. This mathematical relation between Waze variables through the estimation of free flow speed is essential for Flexi. So remember this equation that that will be necessary in the next slides. So the methodology of my model that is Flexi is split into three steps. The first one, transform the information of Waze into a queues. The second one, take these queues given in meters and transforming the number of vehicles in the queue. And the dynamic model that is presented in the step 3 use this information that is the queue of the vehicles, but also the traffic light plans with the time of green time and red time on the traffic lights. At the end, you can find the flow of vehicles. And if you check here, the input of this system are the Waze data and the traffic light plans, and you can estimate the flow of vehicles with this information. Check it also that the queue given in method is possible to measure in the field, but this another queue given in vehicles is so difficult to measure for manual measurement. So it's necessary to clarify that this flow of vehicles is given in passenger car equivalent, because with this information of the speed, it's so difficult to estimate the configuration and the rates of the kind of different classes of vehicles. So my contribution here is this model that provides information of the flow taking into consideration the Waze data. So let me show you in more detail each step. This first step that is transform the Waze data into a length of the queuing methods. I present this linear representation that the meaning of this representation is that the speed decrease as the length of the queue increase. So this is the linear representation. Here I include the parameters for the maximum speed and the minimum speed. So this is so similar to the fundamental diagram. So in the next step, I decide to consider a quadratic function that is present in equation 3, that taking into consideration that the vehicles inside of the queue are moving, and when the queue increase, the vehicles inside of the queue are moving also. So the space occupied by that vehicles will be increased. So this explanation will be tested in the case of study. So for the flow of the vehicles, that is the last step, I decide to formulate this dynamic equation based on one pieces of shooting But this is a simple equation that say that the Q in the next step for a link between the X and Y intersection for the K plus 1, I mean the next step, is based on the previous step that Q in the previous step that I call Q old, plus the accumulation of the vehicles in a cycle time of the traffic light in the intersection Y. So this accumulation is the difference between the inflow and the outflow. So for the calculation of this Q, that is QO, I consider that ways provide information on their congested scenarios each or every 2 minutes. So the model considered that if in the next 2 minutes don't appear one event of waste, the condition of the previous Q come back to the initial conditions. That in another case, it's possible to consider the previous calculation of the equation 4. For the outflow, I consider a common expression that is from the capacity manual, that is considered here as saturation flow and the ratio between the grid time and the cycle of the traffic light. So finally, solving the inflow for the equation 4, I can to estimate the inflow of the for one link. So if this problem is right in this form, that is a nonlinear model that depends on the states, the inputs, and the one vector that is a vector of parameters of each link, we can to formulate an optimization to find this vector that is a parameter estimation regarding to the minimization of the relative error between the estimations and the measurements, obviously considering as a constraint the model. So I want to present this case of study. It's a simple case of study only for test the hypothesis. Is in one corridor in Medellin. I decide to put this demand in one micro simulator that is called Sumo. That is that simulator is an open source simulator developed for the German Aerospace Center and is very useful for the traffic applications. With this profile of demand, I found the first step that checked here that is Sumo in black points and flexi response, and the quadratic that is referring to the second step that transform the queue of vehicles in the leg of vehicles to the queue of vehicles. Maybe here it's possible to relate only a linear relationship, but maybe if the link is longer, maybe you can find this approximation. So for the results for the 3 steps, that is the flexi, check here that under congested scenario that is on saturation, flexi follow close to the Sumo results, but in other cases is not so good approximation. But remember that waze only provide information under congested scenarios. So Sumo emulates the behavior of waze in this case. The adjustment of this case was of 77.5%. So this is a real case of study, and it's a representative case of study that I implement in the city of Medellin, thanks for an agreement between the National University and the government to allow us to implement Flexi for 38 signalized intersections that contains 114 links and a total area for 4.5 square kilometers. This is a real contribution because the calibration of this network, of this part of the city was so hard. So the idea here was the first challenge of this methodology for the calibration was to collect the data in the field to implement the optimization for the parameters. But that data must be collected in the field while waze reports event that both of them events, waze events and collecting data in the field have to be at the same time. So with this contribution, I created a methodology to estimate what are the best periods of time to make that experiments. So the experiments were developed thanks to a team of almost 30 persons that help us to take information. But also I implement and I developed this traffic sensor that is an application, a mobile application to take information and to synchronize the information of all members of the team. This is a contribution because this application was registered and was implemented in the real life. So here is a simple example how was taking that data. For example, this model of traffic sensors for the flow was at the beginning, at the to the end of the intersection. And another person was taking information about the traffic light here in the crosswalk. And another person was taking information about the maximum length of the queue every traffic light cycle. So these people here was moving along the street to capture this information regarding to the previous measurements and tagging with cones along the streets. But for the collection data, I present here this histogram that represent the data collection times for the all 114 network links. So he present that, for example, almost 36 links was possible to collect 5 hours of information. So the challenge here was what happened with the motorcycles. Here in Medellin, there are a lot of motorcycles. Almost 50% of the vehicles are motorcycles. But checking here, that is only a draw, but the motorcycles are in the middle of the vehicle. So it's so interesting effect, but the motorcycles are also in front in the cross wall. And the position was considered because we test with a technology that is called SPNet, that is a big analytic system that counting the vehicles. And if you check here, the motorcycles that are counting are in the middle of the vehicles. So the conclusion here was the motorcycles do not affect the length of the queue, but the capacity of the roads. The capacity of the roads of the another kind of vehicles, the heavy vehicles and the private vehicles, the capacity is less than in other cases. So another challenge here was regarding to the step 1 that relate the speed with the length of the queue that I present here, this information. Check it, this example for a really big, almost 2 kilometers event of waze with the same mean speed and with the same delay. It's so difficult to estimate this part of the street with the aggregated information. But check it here that I present the speed. This is the speed, but this is the data collect by us with traffic sensor manually. Check it that the speed increased, but at the same time, the length of the queue increased. It's not so it's extreme, that situation, because if the speed increase, it's clear for in our mind that the congestion is disappearing. So in this case, was a key to check this information about the length of the event that increased in that time. So the conclusion was that an increment of in the mean speed report by waze does not necessarily mean that the mobility conditions are improving. On the contrary, they could be worsening. It all depends on how far is the current speed of the free flow speed assumed by waze for the road section. But remember that at the beginning, I said that the free flow speed will be so important for Flexi. This is the moment that appeared the free flow speed for us making and solving our problem. So this new variable that is the delta speed was included in the estimation of the length of the queues. And if you check here, the plotting, this new variable, the delta of speed increased at the same time that the queue increased. So this was the best approximation that I could do. So the results of Flexi is present here for only 2 links, but here is compared the measurements and the Flexi data provide the data provided for Flexi. So here in the first row, that the queue of vehicles are measured for the length of the queue of vehicles, and the comparison with Flexi results are really good. And remember that the queue of vehicles given in vehicles, it was not possible to measure in this case, but the other ones, the outflows and the inflows, that is called the demand, is so close for the measurements. The relative error here for this case was 3.7%, and in another case was 13.7%. If you check here, the relative error could be apparently is so big. So in this case, for example, the median is 12.7%, that is here. But there are some values that are the relative error is so big. But the key of understand this relative error is to plot also the absolute error, that the estimation is making every cycle of the traffic light. So the estimation given in the absolute error here is vehicles per minute per lane. The minute is also because it's the mean cycle of the time of the traffic lights. So here is also the error is not so high. Check it that the median is 0.44 vehicles per minute per lane, and in the percentile 90 is less than 1 vehicles per minute for lane. So the last challenge that I came to solve was the representative collaborative data was only found for 39 of the 114 streets in the case of study. It's clear that, for example, here in the avenues, for example, in the Nutivara Avenue, the controllers are programmed by the green wave methodology. So it's almost impossible to find congestion here, there, and the waze doesn't provide information in that corridors. So, but what was the solution? In so many cases, it's possible to present congestion in the Nutivara with another corridors that don't have, that doesn't was possible to find the parameters. So my solution was an implementation of a parameter cloning strategy that allows assign parameters values to those streets, the no report waste data during field data collection. This is a grouping the streets with similar characteristics. For example, the average flows, the number of lanes, the topologies, if that street has turning to the right or to the left. So this is a contribution because with this methodology, all of the links have now parameters to the implementation in real time. So going to present the integration of available data sources, that is the problem 2. And this is clear that we need to apply some or to describe some matrices first. This matrix is dependent of this set that is capital E with a set of n edges. So for this set, it's possible to construct this matrix that is a binary matrix that contains ones if, for example, in this case, the H2 is connected with H1. In another case, will be zeros. But also I define 2 origin and destination matrix that are diagonal matrix. For example, here this O sub n is 1 if the Hn is an origin, or in this case, if that H is a destination. So with this information, it's possible to estimate the flow, the inflow, and the outflow. For example, the inflow is reporting.
Yeah. Okay. Continue, please. And yeah.
Okay. I have reported. So for the inflow, it's so important to consider the origin matrix and the C-in that is obtained from the columns of C, and the outflow is the destination matrix and the CO that is obtained from the rows of C. So the most important thing here is this vector that is the origin flows and the destination flows, and this another one is the connection flows. So these connection flows could be also estimated like a turning rates. Also, that is the flow that is coming from an edge and is going to another edges. So this model that is present in the equation 12 combine to the previous equations. So remember that X is our objective to estimate. So combine the information about different data sources. For example, it's only an example here. I present 4 that the subscripts depend on the kind of data source. For example, here for 1 is Flexi, for 2 is video detection system, for subscript 3 is the OB matrix data. Obviously, this matrix data is not present through flows. It's necessary to make an assignment process. And the fourth subscript is regarding to the historic data. If you have the measurements about this kind of data sources, you can compare these measures with these estimations. How? In this optimization problem that compare the measures with the estimations through the norm edge. This model is the balance of the flow that contain that constraint that is regarding to the vehicles that are leaving one edge.
Por la calle ya no puedo salir.
Necessarily to go to the another edges. So this is to balance the flow, but because it's necessary to fulfill these conditions. But the edge in matrix is a diagonal of matrices. And for example, for the for one of them, matrices that are regarding to the data sources, for example, for the data source I, that data source have the inflows and the outflow information. For example, the inflow information in the diagonal represent the sigma represent the error standard deviation for the inflows and outflows of the data source is I. So this problem of equation 23 could be represented in only one line through this optimization problem that weight the both objectives, that how close is the estimation to the measurements and the fulfill of the balance of the
Sorry about that, it's a hacker, so
it's done.
okay.
Okay. This example is an example using real data, and the objective was to test the methodology. So here I'm going to present an schematic of 3 intersections. So I decide to tag each edge with a number, and the inventory of variables here for the inflows and the outflows are presented in this table. So checking the origin and destination are present for all of them. This information was obtained through a simple assignment process using the matrix, OB matrix provided for the Professor Ivan Sarmiento, that was coming from the OB survey that was provided by the government. So the BDS was located in some particular parts of this system, and the flexing was obtained using the waze data. So, however, it was so difficult to obtain measures in all the streets. It was only possible to find for 4 variables, but this is the exercise to consider the measurements like our reality. What in the pandemic situation, what the project have to stop. So the idea here is to combine the Flexi, the BDS, and the all the information and compare with the measurements that I have. So check it here that the measurement flow is for the offload for the one link is present here in black line. The other ones are the OP flow in yellow, the BDS, that is the video analytics system, in green, and the Flexi in blue. So check it that here, for example, what is the best combination among that data that provide one flow that is called the balance flow that will be close to the measurements. So the idea here was to combine this information, and I present in this table the mean square error between each kind of data comparing with the measurement. So in this case, check it that the matrix has the higher error and the Flexi is the less error here, but the balance flow is also better than Flexi, but is obviously using Flexi information. But the conclusion is the balance flow, that is the fused flow, improves by 12% concerning to the best case that was Flexi. So some application of Flexis could be the OP matrix calibration using the estimations for the flows, the real-time traffic light optimization, the scenarios evaluations using digital twins for congestion and emission, for example, using Flexi as an input for Sumo. But at the end, Flexi is so important because it helps to make decisions. The information is the first step to make decisions. So how to work on large scale scenarios. I present here how is my architecture that I designed to implement the Flexi and the data fusion module in the best way. That I have several modules that are connected by a traffic event server. Flexi is developed by actors that have one actor per street. That ensure that if one actor fails for any reason, all the systems keep working. So the idea is to present this architecture to check how the relation between the models that provide information, that clean the information, and how is the connecting between that models that is a contribution. And also this architecture is connected with a graphical use interface that is now running in real time for the city of Medellin. And also Flexi is connected with Monstro, that is a multi-objective system for a traffic optimization. And Flexi provide information to Monstro to suggest the best plans that can be in the current time. So the conclusions of this presentation are the following. Flexi was implemented in a representative case of study for the flow estimation with remarkable results. As alternative to calibrate the streets taking waze data, it was necessary to implement a methodology for parametric cloning using previous calibrated streets. This methodology must be validated. This will be in a future work, but the idea was is the first step for this methodology. A data fusion methodology was proposed to integrate the Flexi and data with another kind of data like offline and offline information. The test was made using Sumo, but a real case of study was a small one, was used by test this methodology. But at the end, as a result, we have the Flexi is now a product with a software registration. Flexi is operating in real time and helps to make some decisions on the mobility authorities in Medellin. And Flexi is now is using for an input for a real-time optimization system for a traffic light planning that is most. The research outputs of this thesis. I make 3 publications, 1 book chapter and 2 journal papers, and I make 4 national conference and 4 international conference where I present the results of my research. And I have 3 software registrations that is flexible for the estimation of the flows based on collaborative information, the traffic sensor for collecting data, and the Monstro that is for suggest an optimization of urban traffic planning, of the traffic light plannings. So I have 4 dissertations, 3 of them were international dissertations, and I currently have submitted this paper that contains the main results of Flexi. So I would like to give some acknowledgement. This thesis was partially supported by Conciencias through the program Doctorados Nacionales, thanks to Sapiencia that formed a part of my internship, and a special acknowledgement to the Secretary of Mobility of Medellin and the Traffic Light Operation Engineering Center of Medellin for sharing the data and allowing us to implement the monitoring system in a sector of Medellin. I would like to thank to my director, Jairo Espinosa, for helping me to start in my research life. Thank you for sharing with me the last 9 years. Thank you to the professor Ivan Sarmiento, who introduced me in the civil engineer world, and was so interesting because my bachelor was in control. So thank you to Professor Bart, because he was my internship tutor in the TUDALF, and he made me a part of his team, and was so interesting experience for me. Thank you, Felipe, Alejandro, Hector Botero, Julian Ruiz, for pushing me to start my research life. Thank you to my research group that is going out. All of them were part of this process, especially to Andres, David, Juan Pablo, Esteban, Jorge, and Victor. That is my team that it was part of this process to the implementation of thanks to them was possible to make a real-time system running now. And finally, thank you to my family, my parents, Dora and Jaime, and my sisters, Selene and Alison, for your support. And finally, thank you, Ayatollah, my partner, for her unconditional support. Thank you to Samuel, my son, Juan, Maria Angel, Simona.
Pros and cons, what you do. So state that very clear in the thesis, and that will help to have a better document for your papers and so on. Okay, I don't have more questions, but now we grant the word to the director and co-director. So Jairo, go ahead.
Carlos, many thanks. Can you hear me there?
Yes.
Okay, first of all, I would like to thanks all the remarks and feedback that we have received along not only the presentation but during the whole evaluation process, and I think they all put they all come, let's say, not on the basic stuff of the thesis, but really on the go really deeply on the new elements that are set by the thesis itself. In that sense, I would like to put some remarks in a way that this thesis has grown. It has grown more from the point of view of we have to make use from different sources of information in order to assess what is the real state of a city network in order to take decisions for a traffic light management system. That's basically the idea that is behind this thesis. And then we start to collect in some empirical way some data, and also try to reverse engineer some of the elements that are put in there. Some of the work was really hard because if you look, probably the main source of information is of course coming from cell phone data, but it's not directly fed into our servers. What we have is indirect data that is coming from waze, and waze provides a service to the city that is limited on the kind of information that they provide. Besides, they are very jealous regarding, or should I say, they keep their information behind regarding their algorithms. So it demands quite some experimentation in order to assess how the algorithm was working. Based on those hypotheses, we start to make the validation on the ground, using the technology and mixing some of the results that we have already obtained in the modeling part, and then we try to match all this information together, and the result was, let's say, the basics of the algorithms that Christian presented. Later on, we have this remarkable opportunity to roll out the technology, and then there was quite some strong effort by the end of 2019, where most of this technology has to be implemented on software, where we combine also some other techniques that we use for image processing in order to make a good counting of the vehicles in the intersections, and basically we put together also all sorts of technologies. I would like to remark in that sense that this thesis has achieved from the practical side quite a lot. Most of these studies end on the basic experimentation, maybe one intersection or two intersections, but this was a very extensive project that was rolled out on the city, and this gives quite some good value to the results of what Christian has mentioned. I would like to use my time to thank especially Bart and Ivan, because they are part of the seed of all this research area in our group, and from the early stages they give us quite some good support to Christian and to the whole team, and of course to the Secretary of Mobility, because they trust us to put this technology in place and make it work, and as it is working nowadays. So those are Professor Ivan Sarmiento. Thank you, Carlos. Thank you, all the jury.
Hey, thank you, Jairo. Ivan, go ahead.
You listen well now?
Yes,
it's much better. It's much better. So,
okay.
So I think you have to get closer to the microphone.
I'm going to speak aloud. Yeah. I think that this thesis has connected the work of collaborative data with the work of control of a network behavior in terms of predict several variables like queues and flow. I think Flexi is a specific product that solves some of the necessities for variables to control traffic with heterogeneous data or lack of data. Unless of the simplification that are necessary in every model, I think that Christian solved in an elegant way the problems in every step. And all the suggestions that were commented will be included in the...
Allow him to enter again, but... Okay, I don't know what happened with Ivan. But let's finish this. It's lunchtime, so okay. So we again appreciate your presence in this session. After the deliberation of the jury, we inform that you have been assigned the approved grade in the thesis doctorate engineering, civil engineering presented by the student Christian Robillo Portilla Caicedo, and directed by the professors Jairo José Espinosa Oviedo and Ivan Reinaldo Santos Dozuelo. Moreover, the jury considered that the work was